All right, people. So today we are looking at two Hess's law problems, and they're right out of the textbook. It's chapter 6.3 from Zoom Doll. So let's check this out. All right, so um, let's read this problem. There are two forms of carbon. There are graphite, the soft, black, slippery stuff found in your lead pencils, and they're diamonds, the pretty little gems. Now, the enthalpies of combustion, right, for graphite is negative 394 kilojoules, and for diamond is negative 396 kilojoules per mole. They want us to calculate the delta H of converting graphite to diamond. All right, well, how do we do this problem? Well, we have to write out the equations, and I already have them written out. But the combustion of graphite, so graphite reacting with oxygen makes CO2, and diamond reacting with oxygen makes CO2 as well. But what they want to figure out is how much energy is required, how much energy is released in this whole process. Now, this process of going from graphite to diamond is a very difficult thing to study because this reaction can take thousands of years. It happens in the earth. But if you can do reactions that will lead to the same products, like say you do a series of chemical reactions or a series of chemical processes, whatever, to go from graphite to diamond, if you just add them up, well, you'll be able to calculate the delta H, and that's the benefit of Hess's law. But let's continue. So, going from graphite, the combustion of graphite releases 394 kilojoules, and the combustion of diamond releases 396 kilojoules. Well, when we approach these problems, what we really want to do is check if our reactions match up in their location, right? The reactants are on the reactant side, the products are on the product side. So we see graphite is on the left-hand side, and graphite's on the left-hand side here. That's awesome. And diamond is on the right-hand side, or on the product side, but it's on the reactant side here. So it means we have to flip it. We have to flip one of these reactions. So this diamond, we want it on the product side. So we actually have to flip this reaction, and I already have this reaction flipped over on the side over here. So it's the same thing, we're just flipping it over. Now you get out of here. But whenever you flip this reaction, you change the sign of the delta H. You have to multiply this by a -1. And I'm going to go ahead and do that. Multiply it by -1, which makes it 396 kilojoules positive. A positive kJ. All right. So now that it's flipped, we can combine them using Hess's law. Look, the CO2, since this is on the product side and this is on the reaction side, it cancels. The oxygen, reactant side and product side, it cancels out. And the only thing left over is what we want. We want graphite on the left, and we want diamond on the right. So when adding these two equations, once it's been rearranged, that means we can add up the delta H's and find the enthalpy value of this reaction. So let's go ahead and do that. So let's add them up together, and it's not hard to add this up. 396 positive plus -394, that's equal to 2 kilojoules. So in order to get graphite to turn into diamonds, you got to input, because it's positive, 2 kilojoules or 2,000 joules of energy. All right, it's a process that requires you to put energy in. All right, and then that's basically it. So all you have to do is rearrange your equations, and then when they add up, everything should cancel except for the two things you're looking for. Or not the two things, except for the equation that you're looking for, okay? So we're going to do a problem. Where it's a little bit more slightly complicated, right? It's a little bit more complicated. It's a little bit. All right, but let's try this out. Now, when you're doing these types of problems, what I highly encourage you is to, um, well, underline things that are in the correct place, right? So let's read the question first. Diboron is a highly reactive boron hydride that was considered as a possible rocket fuel for the U.S. space program. Calculate the delta H for the synthesis of diboron from its elements according to this equation. Well, this equation can be obtained from adding and subtracting and rearranging and multiplying by things on this example, okay? Whoops, shouldn't have been there. All right, spoiler alert. Okay, so let's check this out. Let's first make sure everything is in its correct place. So there's borons on the left side. I see the borons on the left side. They're in the correct spot, so I'm going to put them in blue if they're in the correct spot, red if they're not. I see the hydrogens. Okay, there's a hydrogen right here that is in the correct spot. Wrong number though. There's 3 and there's only 1 right here, so we got to keep that in mind. And then the B2H6, that is in the incorrect spot. This is over on the left. So that's telling us that we're going to have to multiply these delta H values by a -1 so that we can flip this whole reaction. Okay, but let's do that towards the end. Let's just kind of start off here. What we really want to do is we got to get rid of all that extra junk, all that garbage. Where was my delta H's? I had the, whatever. All right, so let's try to get some things out of the way. Let's see. It looks like these waters are going to cancel, which is a good thing. Maybe let's start with flipping this reaction, right? We want to flip this reaction so that the B2H6 is on this side. So let's multiply this by a -1. I was on the right track. Let's start off with that. So let's move things around, right? So the B2O3 is going to, let's rearrange these things, and I'm moving things around. So now we've flipped this reaction, and if you're following along with a sheet of paper, just pause it right now so you can rewrite this. But now it's in the correct spot. The B2H6 is in the correct spot, which is awesome. All right. But now let's continue. Let's see if we can get rid of certain things. So for example, these B2O3s, they're going to cancel each other out. That's good. But wait. What about these? I said earlier, that needs a 3. Let's do that. Let's multiply this whole thing by a 3. So we're going to get this whole thing and we're going to multiply it by 3. All right, let's go ahead and do that. And I think I have a, I guess I don't have it written out. So let's multiply this whole thing by 3. So we'll see. Okay, that becomes 3H2. And then this becomes 3 halves O2. And that's going to be 3 H2Os. 3 H2Os. Okay, so now our H's are looking good. Our O's are looking a little interesting. But sometimes, even though there's fractions, don't get scared. Look, 3 halves plus 3 halves, that's 3. So that's 3 on the reactant side, and there's 3 on the products. So what actually is going to happen is, well, this is going to cancel out with this. So we're not going to really have to worry about that. And look, that B2O3 is going to cancel with that B2O3. These 3 H2Os are going to cancel. Whoa. 3 H2O gas, and there's only H2O gas right here. Okay, so we're gonna have to multiply this one by 3 as well. So we're gonna get this right here, multiply it by 3, and let's go ahead and put the coefficients now so that we can see. Well, this H2O is in the reactants and this one's in the products, so it's gonna cancel out. And look, now we have H2O liquid. There's 3 of each. So these can cancel too. And now let's go and let's check if everything that we need, we said should be in the correct spot. This H2s, B's, boom. The three things we need on their correct spots, everything else is canceled, which means all we have left to do is add up all of our delta H's. So let's go ahead and do a little bit of math. That 44 times 3, hello, calculator. ¿En dónde estás? 3 times 44, that's equal to 132 kilojoules. Negative 286 times 3, that's 858. Negative, don't forget your negative, Mr. Sanchez. And then this one I can do in my head. But I'm using my calculator anyways because I'm not sure of myself. All right. And then over here we have a negative 1,273 kilojoules. Once we check that all the units are the same, let's add these all up. So let's start off. We got negative 1,273 plus 2,035 minus 858 plus 132. And we end up getting 36 kilojoules. And this right here is our delta H. And if we wanted to be a little bit more specific, since this makes 1 mole, right? If you look at the coefficient in this reaction, it is a 1. So this is actually 36 kilojoules per mole. But if there was a 2 there, you can divide it by 2 so you can get your per mole. But that's basically it for our delta H. This is how you do Hess's law. Now, a few things that I encourage you to do is, I know I'm a little messy, but I think if you underline a bit of your work, try to keep reactants on the correct side, products on the correct side, and just make a little note when they're actually there. These types of problems require a lot of space, so don't be afraid to waste paper. It's already dead. Don't worry about it. You're not going to hurt that tree anymore. Just use it, okay? Use your paper. Be as neat as possible. Don't crunch it up into one little spot. If you do, it's going to bother me when I check your work. And also, it's going to bother you when you check your work. All right? But hopefully this helped. And if it didn't, send me a video of someone who did so I can see what they're doing right. All right? But take it easy. Hasta luego.